All right, we're going to talk about Bernoulli's principle to wrap things up. It's basically just conservation of energy for fluids. So if you look at the work equals delta K plus delta U. So F dx is going to be equal to F over A dV is equal to 1/2 delta K squared, or delta K plus not 1/2 delta K just by itself plus delta U. So P times dV is going to be equal to 1/2 M divided by V dV times delta V squared plus rho dVg delta H, because that's again M divided by V times V. So when you follow the algebra for this, you find that P1 minus P2 times dV equals everything on the right side. Divide through by dV and find that P1 minus P2 equals 1/2 rho delta V squared plus 1 rho G delta H. So 1 P plus 1/2 rho V squared plus rho GH is a constant, is what this is saying. So that's basically all you need to know about it. There's a couple uh, useful values. There's a couple things that come out of here. So uh, have if you have different heights, first of all, notice that this height is goes up as z goes up as you go up in height. H also goes up in this case instead of the other way around, which we had it where h was going down for an increasing h. And then P equals 1/2 rho V squared plus rho GH is equal to constant. So if you have the same velocity at both points of the equation, both points that you're looking at, then P plus rho GH equals P plus rho GH, which just tells us that delta P equals negative rho G delta H, which gives us our initial equation for the pressure of a different system. So yeah, this is good. There's one more thing that I actually forgot about that I want to talk about, which is just the continuity equation. Continuity equation, which states that for an incompressible liquid, where the density of the liquid, the density of the fluid is always going to be the same, then as you go through two different areas, with A1 and A2, then mass dm1 dt equals dm2 dt, because the amount of mass passing through each one has to be the same. So rho times A times x d rho ax dt is equal to d rho 2 a2 x2 dt. And let me just say that let's just get rid of this rho 2 because rho is constant. That's one of the uh, assumptions that we made. So A1 times dx dt equals A2 times dx dt, dx1 dt, dx2 dt. So A1 times the velocity of the fluid is going to be equal to A2 times the velocity of the fluid at the different points. So if you have a really small bottleneck, like you see in the first area, or the area to the left, then what you're going to see is that the velocity will be going a lot faster than it will go through like the thicker, the wider tube just down the or the wider area just down the tube. So that's the continuity equation. Another thing to bring out is I don't remember whose equation this is. It has a name, but basically uh, a change in pressure somewhere in a fluid causes a change in pressure everywhere in the fluid. So if you this doesn't say that pressure is constant. This doesn't say that pressure is constant across the fluid. It just says that if you press down, if you press down here, then that's also going to have a change in pressure, obviously over on this side, but it keeps going over and over and adapting a change in pressure everywhere in the material. So what this means is that P1, so pressure in one area, uh, change in pressure in one area is equal to change in pressure in another area, or force 1 over A1 is equal to force 2 over A2. So you can have a little bit of force pressing down in an area with a small, or yeah, you can have a little bit of force pressing down in the area with a small uh, cross-sectional area, and that's going to cause a change in pressure all the way through this. And then that force, that extra force is going to be greater as you have the greater area. So this is called the hydraulics equation in addition to whatever principle I'm forgetting right now. But this is how hydraulic lifts work. Okay, so that's basically all I have to say for today. Glad to see you there. See you on Wednesday or on Monday, and fair warning that this is going to be a 60-point not exam, a 60-point lab report. So it's a formal lab report, the second one of the semester coming up. All right, see you on Monday.